Well, welcome back, guys. We are going today to talk about 1.4, which is first order linear ODEs. So, here's our form for a first order linear non-homogeneous ODE in general for a dependent variable y as a function of an independent variable x, right? And so we look at this guy and we're just like, okay, well, if that wasn't there, this is a super simple first order ODE because all you do is integrate, right? Integrate with respect to x and life is good. So this is in the way and of us just straight up integrating both sides, right? If that y wasn't there, life would be good. But the y is there, and we're not going to get away from that. And so what do we do? Okay, we're going to try to find a way to just integrate this equation. That's kind of the deal with a first order linear ODE. And one of the things mathematicians do a lot of times when they're kind of stuck and they've got nowhere to go is they're like, well, what would happen if I just multiplied that equation by some unknown function? If I had some other function kind of working for me and I could kind of do something with that function, maybe it could help me out. So that's our goal, right? We're going to multiply the ODE by an unknown function and I'm going to use u of x. Okay, some books use mu of x, and our book we're using right now uses r of x, but I'm going to use u. Okay, all right. So if I do that, if I multiply this equation by u, and so what's our goal? Okay, we're going to find a good u later, right? He's an unknown function. Find a good u. Goal. Okay, later. Find a good u. Well, how are we even going to say what's a good u? Okay, well, that's coming up, right? But it's an unknown function, right? What have we been doing in this class with unknown functions? Maybe we might be able to find some equation with the derivative for that unknown function. All right, anyway, let's not get too crazy and jump ahead. Let's just multiply our differential equation by an unknown function, okay? All right, and so what do we got? If we do that, we're going to have u of x times y prime, right? And I'll just write y prime of x, it's the same thing. Y prime and y prime of x, same thing, right? Plus u of x times p of x times y, right? Is equal to u of x times g of x. Yes? Okay, good. All right. So we look at this equation and we're like, wait, why is that any better than this equation? This one looked a lot simpler. But hey, wait a minute, right? Remember what we wanted to do. We wanted to just try to integrate, right? And as we started writing this down, u times y prime plus stuff times y. U times y prime plus stuff times y. Is that ringing any kind of bell to you all? Right? Think about your calculus rules. If only right? If only what? If only it was true that, well, the first times the derivative of the second plus the derivative of the first, u prime of x times the second, if only it was true that u prime of x was actually equal to u of x times p of x. If that were true, then this left-hand side would be a pretty cool thing, right? Now, remember, we brought in this unknown function, so we could make up things that we want to be true about it. So we're going to just put this in a green box here, and we're going to say that's true, and proceed and see what we get. Okay. Star is true. Okay, so with that, then what do we have? U times y prime plus u prime times y is equal to u of x times g of x. I'll just write it out there, okay? Everything depends on x. What does this look like? Yay, right? This is the product rule in calculus. Yeah? Product rule. Just writing things slightly differently just to get you comfortable with all of it, okay? What did we do? We replaced this with u prime, right? That's our green star. Okay, well, what does the product rule say that is equal to? I'm going to write it in primes, and then I'm going to write it in without, with more derivative notation. So what is this? First times the derivative of the second plus derivative of the first times the second. Good, that's the derivative of the product. U times y, right? Yeah, that and that are the same. So that is equal to this. So if we have this new crazy function u that we multiply the equation by, and then we have this requirement on u, then we turn the left-hand side of that equation into a total derivative of this quantity, and now what's over here only does depend on x, and so we actually can integrate, right? So let's just make sure that we recognize that prime means derivative with respect to x, right? And so we have a derivative with respect to x. Another way to write it, this is just the same thing to make sure you know all the different derivative notations. Derivative with respect to x of u, which depends on x, y, which depends on x, right, is equal to u of x times g of x, right? So now what can we do? Well, we can integrate, yeah? Integrate both sides, right? Fantastic. This is a derivative with respect to x. We're going to integrate. Here, we're going to integrate, right? Okay. And when we do that, what do we get? What do we get? The integral here is u of x times y of x, the integral of the derivative, right? And then here, what are we left with? We've got the integral of u of x times g of x with respect to x, right? Plus the constant, yeah? Okay, and now what were we looking for? What was our original goal? Well, original goal is this ODE. What is this ODE asking you to do? It's asking you to solve for what? Yeah, y is a function of x, right? That's what you're being asked to solve for. The unknown function in the ODE. That's where we started. So what should we do with our equation we have here? Beautiful. Solve for y. How do we solve for y? We divide by u of x, right? So y as a function of x is 1 over u of x times the whole thing. The integral of the product of this unknown guy that we just introduced with the right-hand side of that guy plus this constant and 1 over that. So here is a formula, right, for our solution, an explicit formula, provided, you know, this integration can happen. But we have this magic u function, right? So where did u, what is the deal with u? If we could only come up with what exactly u is, because right now it was, you know, it started as this unknown function. Boy, if we only had some equation that would give us u, right? Okay, all right, I see you all excited. Okay, so we've seen what we just did right here. So what we're going to do is derive a general formula, but it's the process that you really want to think about. It's harder to memorize the general formula. You want to be able to actually follow out the process, okay? Oh, don't erase the big green box, yeah? So, how are we going to find u? How will we ever Okay, what was in our nice little box was, and I'll put it in blue just in case the green isn't transferring real well. We had from our nice green star there that u prime of x was u of x times p of x, right? That's what was in this box right here. Okay, so that's who we're shooting for, how to find this guy, right? What is this? Good. First order ODE for u as a function of x, right? Okay, so who is our dependent variable here? Good. U. So we're taking the derivative of. Who is the independent variable here? Good. X. That's what we're taking the derivative with respect to. Who's our unknown function? U as a function of x, right? That's what we want. That's what we want to solve for. What is this guy P? P of x is just some generic function that's in our equation. It's some function of x, right? Some unknown but given, right? Unknown but given function of x. Not this unknown function that we're interested in solving the differential equation for. Okay. So P of x could be any function, but it's some specific function that we're thinking about. It's not the solution of the differential equation, right? Okay, so what do we do? How do we solve this guy? What else is he? He's first order, right? Yeah, good. Linear, right? Well, that's great, but that's not going to help you. He's homogeneous, okay? Autonomous? No, right? Because this guy makes him not autonomous. It's great that it's first order linear, but it's not going to help you solve it because we don't have a solution for first order linears yet. We need that function in order to get first order linear. So what is the only other type of equation we know how to solve? Good. You got it. It's separable. Let's see how we would separate it. So let's write this. This guy is in prime notation. Let's write it in the longer derivative notation. So how would I write u prime of x? The derivative of u with respect to x. Beautiful. Exactly. Right? And then, what is that equal to? Well, u of x times p of x. But, now, like, spelling out that u depends on x is kind of redundant at this point, right? We know that, yeah? We get it. We understand how this works. So we get du dx is equal to u times p, right? Well, now it's good to remind yourself p is some function of x, yeah? Okay, so what do, right? This is this equation just rewritten. And what is the other vocab word we haven't said just yet? Right, this guy is separable. Yay! Last section, right? 1.3. Okay, so how do we separate the variables? We get everything involving the u's on one side and everything involving the x's on one side, right? So what is the differential form that we want to write this differential equation in? It's in derivative form. We want to put it in differential form. What's the differential form going to be? Good. du over u is equal to p of x dx. Yeah? Good. Awesome. So now what? Now we have the variables separated. It's in separated form now. All the u's on one side, all the x stuff on the other side. So what can we do? Right? We can go ahead and integrate, right? Yeah? So what is the integral of du over u? We should be pretty good at this by now, right? Natural log of absolute value of u, right? That's what we got on this side. And then we've got equal to what? Well, p is some arbitrary function of x, and so you can't integrate it because you don't know what function it is. It could be anything. So all you can say is, well, if I knew p, I would integrate it, right? Yeah? Okay, so you've got integral of p of x dx. Now, if you want, we could add plus, so we can think about putting the constant is just in here with the integration, but let's actually put one out here. So let's just say plus k, right? So as if here we would just do the integration, and here's the adding on the k from doing this integration, the arbitrary constant from doing that integration, and we'll see whether we actually need it. So that's kind of one of our goals as well. So what do? We're good at this too. We now exponentiate both sides, right? When I exponentiate both sides, what do I get? I get e to the natural log of the absolute value of u. So we're good at this now. What does that give me? The absolute value of u, right? And that's going to give me e to the integral of p of x dx, right, on that side, times e to the k, right? But we're super good at this now because we know, right, all right, well, everything's positive, but u could be negative, and so I don't want to have absolute value, and I don't want to have plus minus. And so therefore, if I'm going to lose these guys, and I'm going to lose this positive arbitrary constant, and rename k to another arbitrary constant, and this guy could be positive or negative, and that takes care of it all, right? So here's our u, okay? So now, what were we doing? We were saying, okay, well, let's multiply by an unknown function, right? Find a good u, a u that would turn this differential equation when we multiplied it, so that the left-hand side was just a total derivative, right? The derivative of a product. We also, that makes a good u. It has to do that, but we also want a good and simplest u, okay? Simplest u. So there are lots of u's that would do this, but we just want the easiest one, right? And the easiest one is going to be when we do what? Yeah, make that constant k1, right? Okay? There's infinitely many functions that would do what we just said. We can multiply them all by any arbitrary constant, but we'll take k to be 1 and get the simplest one. So we take k equals 1 for the simplest u. And so what is u? U is e to the integral of p of x dx. That's the function u of x. Where did p come from? You put this in standard form, right? This is the standard form for a first order linear ODE. So when you get all the y stuff on one side, the coefficient of y prime is 1, plus whatever multiplies y, that's the p, right? So that guy is p, and then the stuff that doesn't have y's in it on the other side. So you gotta put things in standard form first, and then we have a general solution straight away for all equations. So I'm just going to rewrite the general solution. Y prime plus p of x times y equals g of x is this equation with this expression in the place of u, right? So y of x is equal to, so 1 over u, if I put that down there, that's 1 over that guy, I have an exponential, so I can rewrite that with a negative exponent and just say e to the negative integral of p of x dx, right? That's my 1 over u, right? 1 over u would be e to the negative integral. Then times the integral of what? E to the integral of p of x dx, yeah? So that guy, that's our u. So that expression times g of x all of that I then integrate. So lots of fun integration here, right? And then add a constant, right? Right, so distributing like that guy would get multiplied to that guy, right? So you can't just like throw the constant on the end. It's not just a plus C, right? It's in the brackets, makes a big difference. Yes? In the brackets makes a big difference. So what does that mean you gotta do for these problems, right? You got to, if you're gonna plug into the formula, you're gonna know the formula, but you gotta identify, you gotta put things in standard form, you gotta identify your P of X, you gotta integrate P of X, right? You gotta then compute U. U is called, oh, I didn't even say this, U is called the integrating factor. Integrating factor. Why do you think we call U the integrating factor? Yeah, because we multiplied it. It was a factor that we multiplied times this equation so that we could directly integrate it, yeah, and turn the left-hand side into a complete derivative that we couldn't integrate. Okay, then you do E raised to that function, yeah, okay? And so then that becomes a function, you multiply that times the right-hand side, and then you do that integration, yeah? Okay. If you're gonna plug into the formula. Otherwise, you follow the process and you come along for the ride, okay? So let's talk about that for a sec as well. So that's pretty cool, right? We just used our separate rule to find our integrating factor. How awesome was that? Yeah? And here we talked about how we didn't need to worry about, when we solved for the integrating factor, we didn't need to worry about adding that constant there. So let me ask you this question. If we do this integration right here, do you need to add a constant when you integrate P? So what would happen if you did, right? If you add a constant when you integrate P, whoops, let's see, say, you know, plus, we're running out of constants. Let's just say plus beta for fun, right? Yeah, okay, if we did that, right, then what? Then this would be e to the integral of p of x dx times e to the beta, where you didn't add the constant, right? E to the beta would just be some constant, right? Beta is an arbitrary constant, so e to the beta is an arbitrary constant, still positive, and so that would be like times beta, right? So that'd be just multiplying our u by a constant again, right? Okay? And similarly, when we came in here, right, you would just get that constant would then come in here, and a constant pulls out of the integral, but then you've got 1 over it, right? And so you would have a constant down here, and those two guys would cancel each other out. When you distribute it across to here, a constant divided by an arbitrary constant is still an arbitrary constant, and so therefore we don't have to worry about these guys at all. Does that make sense? Yeah, you're not losing anything. It's just already absorbed into the solution. Woohoo! Okay, so let's look at an example. Okay, so let's do the homework problem, maybe, ish. Yeah, you think? Let's look at exercise 1.4.6. This is a web work problem. So what do we have? Solve y prime plus 3x squared y is equal to sine x times e to the negative x cubed. Y of 0 is equal to 1. So this is a good initial value problem, right? nicely written for us already in the standard form, right? It's already in standard form. If it's not already in standard form, then you gotta put it in standard form, just like some of those earlier WIPWORK problems. Okay, so what do we identify here? So we got an initial value problem, but first we wanna solve the ODE. We'll do it two ways. Okay, so let's just identify what our P of X is, okay? So P of X is 3x squared here, right? And our G of X is sine x times e to the negative x cubed, right? Okay, P and G. Okay. So, what is our integrating factor? Well, our integrating factor, u, is e to the integral of p of x dx, right? That's what we derived. Yes, it's not magic. We saw exactly where it came from. Okay. Okay, so what is that? For this problem, that's e to the integral of 3x squared dx. Yes? What's the integral of 3x squared? Good. Add 1 to the exponent, divide by the numerator. Beautiful. E to the x cubed, because it's a polynomial, right? E to the x cubed. Should we say plus c, plus k, plus anything? No, right? We already talked about why we don't need to do that, right? Okay, so our integrating factor is e to the x cubed. Yeah? Okay. So we could just plug in to the differential equation. Let's just go do that, just so you see how it would work. But then we'll walk through the process of not doing that as well. So, what is our y of x? If we're plugging in, right? Well, if this is e, if this is our guy, right? U is e to the integral, p of x is e to the x cubed, right? Then 1 over u is e to the minus integral of p of x dx, right? Yeah? Which is e, right? Right? E to the, whoops, I have to turn that off. E to the minus integral of 3x squared dx, which is e to the minus x cubed, right? Which we could have just done from here to here too, right? Just make sure you're all together here with me, right? Okay, 1 over u, e to the minus x cubed, yes? Okay, either way. Okay, so what do we have? Then we would have e to the minus x cubed, right? Times the integral of e, well, yeah, to the minus x cubed, because that's what our guy is, right? That's what came out of our integration. That's our u, right? Times g of x. What was g of x? Oh, right, it's looking better now, isn't it? Sine x times, whoops, not minus. It wasn't looking better, right? E to the integral, right, is just e to the x cubed, right? Yeah? That was our u. Times sine x times e to the minus x cubed. This piece was our g of x for this problem, right? Integrate with respect to x plus c. What beautiful thing happens in this problem? Without this canceling, life would be bad, right? That's just e to the 0, which is 1, right? Okay? Or e to the x cubed divided by e to the x cubed, right? Which is magically why this term was in g of x, to make this integration easier. And so what do I have? Now you're just doing e to the minus x cubed times the integral of sine x dx plus c, right? What is the integral of sine x dx plus, what is the integral of sine x dx? Yeah, what was that? Good. What function has a derivative of sine? Minus cosine x, right? The derivative, you get sine, yes. Our plus c was already there for us, right? we didn't have to worry about that. And so here is our general solution. You can either leave it like that, or it's minus e to the minus x cubed cosine x plus c e to the minus x cubed, right? Okay, so either way, one or the other, no real reason to distribute. Okay, that's plugging into the solution, right? That's just plugging in. But if you didn't just plug in, what would you do? You just run through the steps that we went through to derive the general solution. So let's do that. Okay? So we found our integrating factor for this problem. Same deal, you would still do that, right? That's what you would do, find the integrating factor as defined right here. You know, we solved that equation for the integrating factor once and forever, right? You never have to do that again. We know that this is our integrating factor, right? And so that's something to always remember. You've got to put it in standard form first. And then what did you do? You multiply that integrating factor, right? So what did we get? E to the x cubed. You multiplied it times the original equation, right? And so if we multiply that equation, the ODE, by u, which is e to the x cubed, right? Then what do we get? E to the x cubed times y prime plus 3x squared e to the x cubed times y, right? Just wrote it that way. Still multiplying by, is equal to sine x times e to the negative x cubed times e to the x cubed, just to make sure you see it, right? So here's the e to the x cubed multiplied times every term in the equation, right? And what's the beautiful thing then, right? These two guys cancel each other. One's the inverse of the other. The multiplicative inverse. And so we're left with this, and what is this guy? This is just the derivative with respect to x of what? Yeah, u times y, right? What was u? E to the x cubed times y, right? And so that turns this equation into this, right? By the product rule, the derivative with respect to x of the first, a product of two functions is the first function times the derivative of the second function plus the derivative of the first function, right, times the second function. And the derivative of e to the x, e to the stuff times the derivative of the stuff. Yes? All right. So then what do? Well, we're here, and so we integrate, right? Yeah. So it's actually better not to. I'm gonna you know, better not to squeeze stuff in. I'm gonna just, you know, so we're gonna integrate the derivative with respect to x of this expression with respect to x, and that's we're gonna integrate that expression with respect to x, right? Setting those two guys equal to each other, and the integral of the derivative of this stuff with respect to x is just this stuff. E to the x cubed times y, right? And then what do we have? The integral of sine is minus cosine x. Now you do need to put the plus because you're actually doing the integration, and therefore solve for y. Now solve for y, that was our goal, right? Y was our dependent variable, and so y is equal to 1 over e to the x cubed minus cosine x plus c. If you think about what you probably would normally do, solve for y, you would divide by that, right? But what is that, right? That's exactly e to the negative x cubed minus cosine x plus c, which is exactly what we had right there. Yeah? Okay? So, formula, plug-in, but process, you gotta be able to do the process as well. Yeah? Now, we haven't solved the initial value problem, so let's look at that, right? So now what do? Right? We have a general solution. Any way you look at it, here's our y of x. Okay, I'm just gonna look look at it from right here. And we're going to now apply our initial condition, okay? So what is the initial condition? We want to evaluate y at 0, right? Y at 0, so let me do that. I'm just going to plug 0 into my general solution. What do I get? E to the 0, right? Which we know is 1, good, okay? Times minus cosine of 0, I'll write it there just to make sure we remember this, right? Plus c, yeah? So I'm just plugging into this version of it, right? I could plug into that version, but it's more work, right? Okay, what is cosine of 0? Okay, good. Cosine of 0 is? Okay, good. 1. All right, and so I got a minus here. So what do I got? I got minus 1 plus c. Y at 0 is negative 1 plus c. What do I want y of 0 to be? Okay, I want y of 0 to equal 1. Okay, so there's lots of, we've been putting it out over here. We can like just say, okay, now I want this to equal 1. It doesn't matter, it's up to you how you do this. So what do I want to do? Solve for c. As long as it's clear to me when I'm looking at your work, c is 2, yeah, right, okay. So since c is 2, then what is our solution to the initial value problem? Yeah? Make sense? Now, before we close this up, I want to just point out one other thing. So your book gives you a nice general solution also for an initial value problem. So let's look at that. That's the general solution of the ODE. General solution of the general IVP y prime plus p of x times y is equal to g of x, and y evaluated where? Where's the generic place that we say? Good. X naught, some initial value of x, is equal to? Good. Y naught, some initial value of y, right? So you could plug into this solution and solve for c, and come up with a very similar version of the solution, but let's just write down what that general solution can be given as. A couple of ways to write it. All the same. Ooh, we should talk about that too. Can be written y of x is equal to, well, e to the minus, instead of doing indefinite integrals, your experience with this from before should say, oh, we're going to want to do a definite integral, right? And what's our lower bound of integration going to be? What do you think? Good, x naught, because that makes it nice when we evaluate this at x naught. And then what's our upper bound of integration? Good, it's x. Fantastic, looking at that guy. Okay, so now can I write p of x dx in here? Good, no. Okay, so what are we going to write? Good, p of t dt, sure. Okay, so I'm worked with that first piece, right? And now times what? The integral of, oh, but we got to integrate from where to where? Good, x naught to x, yeah? Of e, the integral from, oh wow, okay. So let's see, we're gonna have this guy, if we do the same thing, x naught to x of p of t dt, yeah, okay. Then when we integrate this expression, we would have this piece is a function of x, right? So then we're going to integrate this with respect to x, so that means we can't use that notation. Does that make sense? Kind of, yeah. So let's think about that. The result that comes out of this is going to be a function of x, right? Because you're going to integrate, you're going to get something in t, and then you replace the t's with x's, yeah? Okay? So that guy's going to depend on s. So what do we want to have happen, right? We need our guy in here. We're going to have to turn this guy into dummy variables if we're going to integrate here from x naught to x, right? Okay, and so if we go with integrating x naught to x and switching our dummy variable to say dt, okay, like we normally would, and then these guys are dt, so g of t, right, e to the integral of, now since in here we need another dummy variable, okay? Because we need this guy to come out as a function of t so that then we can integrate it and then we can integrate that and get back to a function of x. Okay, and so this guy is going to go from x naught, say, to t of p of, I don't know, s ds, right? We have to change that dummy variable as well, okay? Then what will come out of here is a function of t that will multiply times this function of t, and then we will integrate and get a function of x. Yeah. Now the beautiful thing about if we plug in x naught is here we're going to get e to the 0, which is going to be 1. Here we're going to get 0, right? So, erase this. So if we're going to evaluate this guy, what are we going to want to show up here? Or why not? Because everything else will go to 0 or 1. Does that make sense? Sort of? Kind of? Let's see if I wrote it the same way your book did. It would be magic if I did. And in fact, I kind of did, okay? They just use, well, he's using an f of t, and I'm using a g of t, so that's one difference. And here they just use the s dummy variable to be consistent with, but it doesn't matter because it's a dummy variable, right? So we can use t, we can use s, we can use whatever we want, okay? And then if you evaluate this guy, at x naught, you're going to get e to the 0 times 0 plus y naught, which is 1 times y naught, which is y naught. Yay! Right? Make sense? Another fun exercise for you would be to take the derivative of this and see that it actually satisfies this equation. That's sound fun and scary, but think about that, right? So here we see that we have the initial condition satisfied. If you take the derivative of this expression, then this guy is a product of two functions, right? So you would have to use the product rule. The first guy times the derivative of the second guy, and you'd have to use your fundamental theorem of calculus for taking those derivatives, right? Plus the second guy times the derivative of the first guy, right? And do some manipulating, moving things around, recognizing stuff, and hopefully, lo and behold, you can see that that really does satisfy that differential equation. Okay, I think that's all for us today with first order linear ODEs. These guys are super nice. One of the things we'll talk about is their existence and uniqueness of solutions to initial value problems. Think about it yourself, since you really already have the tools to do that. All right, see you soon.